Good evening, and thank you for joining us. Today's webinar is on analysis of petroleum samples by ICP OES, presented by Manny Almeida, our ICP Product Line Manager. We will be taking questions, so feel free to submit those throughout the presentation, and we will address them at the end. Okay, I'm going to hand it over to you, Manny.
Thanks, Shelley. Good morning, everybody. Thanks for taking some time out to attend the webinar. So the subject today is we're going to look at the analysis of petroleum samples or petroleum type samples by ICP OES. Okay, so analysis of petroleum samples by ICPS has been done since the late 1970s. A lot of the original work was done at Exxon in Texas. And the reason ICP is a good match for petroleum type samples or oil samples is it can handle both aqueous and organic samples, sample types, and handle the range of elements and the concentrations that are found in the industry. It's also compatible with many different organic solvents, so you can do analysis using simple dilutions with solvent to fit the different types of samples that people may have to deal with. Right? So the agenda. So what we're going to look at today, briefly, is we'll look at some sample preparation techniques for oils type samples. Talk about some sample introduction, the different nebulizer spray chambers, plasma parameters, to be able to get a good stable plasma so that you can run the organic solvents through it. And then we'll look at some selected methods, and these are basically methods that we've worked on in our lab for potential customers or actual users that were having some issues. Before we get into the subject matter is we are Teledyne Advanced Chemistry Systems, otherwise known as TACS, and we have facilities throughout the U.S. At Teledyne Leeman Labs, located in Hudson, New Hampshire. We have a division in Hampton, Virginia, Teledyne Hastings. They manufacture flow meters, controllers, and vacuum type products. In Mason, Ohio, Teledyne Techmar manufacture total organic carbon, volatile organic compounds, and semi-volatile organic compounds, as well as mercury analyzers. We also, CTAC is also part of the TACS group. They're located in Omaha, Nebraska. They do automation, sample prep, specialty nebulizers like ultrasonic nebulizers. And all our manufacturing is done in Lincoln, Nebraska, where our ICPs and DCR type products are built. Just briefly, if you're not familiar with Leeman Labs, we have been in the ICP business for approximately 35 years. We still manufacture in the United States. For a company that's been around, we've got a number of different firsts. We were the first people to use the shell systems, which are virtually used in all ICPs today. We were also the first to develop some of the larger array type detectors, which are used. Over the bottom left is the list of the ICPs we've manufactured over the years. The ones that are in blue are when we switched over from the classical photomultiplier tubes to solid state array detectors, which are pretty much the industry standard right now. And we actually no longer make any PMT-based systems. So the information and data for samples today the methods that we'll talk about were done on the two ICPs that we currently offer. One is the Prodigy 7. These instruments are available as axial, radial, dual view. They have low argon consumption, and they have the modern CMOS array detector, which we'll talk about very briefly. The second instrument that's used is a Prodigy Plus. Again, it has a pretty wide wavelength coverage. The difference between the Prodigy Plus and most other ICPs is it can have halogen capability. So one of the methods that we're going to look at towards the end of the presentation will be the determination of chlorine and silicon in gasoline. Okay. And sort of common between both systems is the solid-state array detector that we've developed. This is the most modern detector in the industry, made with modern electronics, much faster than the previous ones that we were using, and that helps improve sample throughput tremendously. Very little time is spent transferring data from the detector to the instrument. And also because it's faster, it has much better linear ranges than competitive or older type systems. So that's a standard feature on both our ICPs. Okay, so the agenda, so we're going to take a look at sample prep, sample reduction, some plasma parameters, how to set it up so that you can get a successful analysis, and then we'll look at some selected methods. So the first will be sample preparation. So the preparation methods that are currently used, and these is not an exhaustive list. I'm really going to just speak to things that I actually have done. So I have personal experience doing some of these. So first is decomposition by acids, microwave, and organic solvent dilution. So the pretty classical technique for sample prep in the oil industry was to use sulfated ashing, industry classic. So it's basically a sample dissolution that uses sulfuric acid. It does complete solubilization of the sample. Over on the right-hand side is just sort of very brief, overview, not in detail, but can handle up to maybe 20 grams of sample at concentrated sulfuric acid. It's heated to dryness, then heated in a muffle furnace. Then the inorganic residue is dissolved in nitric. If you want to see a detailed description of the sulfated ashing technique, you can look at ASTM method D5708, which is the determination of nickel, vanadium, and iron in crudes and residual fuels by ICP OES. There's a very detailed description of the sulfated ashing technique in there. Okay. The advantage of this technique is it prevents the loss of volatile elements like sodium, lead, and cadmium. Results in a relatively low sample dilution because you can dissolve a relatively large amount and then dilute it up to a relatively small volume, so you can get some not so much of a dilution effect. It's very sensitive and it's a very reliable method. So that's why it's considered one of the standard or classical methods. The disadvantage of it is time consuming. It could take hours or many hours to get a sample to go into solution, right? You do have the potential for sample contamination because it's basically done on hot plates. And it does still loses some volatile elements, notably selenium, antimony, and mercury can still be lost with this type of a technique. The next potential technique is microwave digestion. So here these samples are subjected to a microwave field. Samples heated in a much more uniform manner than on a hot plate. On a hot plate, you're heating by conduction. Here, you're heating by the microwave waves. So the samples reach boiling point very quickly. The closed vessels allow to have much higher temperatures and much higher pressures. Again, on the right-hand side is sort of basic program for it. So relatively small amount of sample, 0.2 grams, add some nitric acid, power up to 800 psi, and then a ramp up to a temperature, and then a hold. So that's for one particular type of organic sample. Depending on the samples, that may change the exact parameters used. Advantages of microwave: it's much faster. It can be up to 90% faster than other techniques. Closed vessels, you reduce the loss of the volatile species and to reduce the chance of contamination. You have really good control of the temperature and the pressure, so you're going to get reproducible digestions day in and day out. You don't have to monitor it. The process is automated where, when you're using a hot plate and you're adding reagents and things, it's sometimes difficult to maintain the same procedure day in and day out. It does require less acid to get the digestions to proceed, so that's better for your blanks. And again, like I said, samples can be digested without constant supervision. The disadvantages are the amount of material that can be digested on the closed vessel systems. So that's, you're limited to probably a half gram or less. There's some time invested in cleaning and assembling the vessels. And microwave digestion equipment represents a significant investment to be able to analyze or to use high pressure vessels. The advantage, though, is the amount of time spent or saved for manual digestions is more than, the return on the investment will be made once you don't have to monitor or dedicate somebody to preparing all these samples. So there's a good return on investment on there. The next is the organic solvent dilution, and this is by far the most common method that people use. Typical dilutions are roughly about 1 to 10. Sometimes if you use less, like a 1 to 5 dilution, you may run into some nebulization and volatilization interferences, even if you use an internal standard. So, a 1 to 10 is pretty typical. Some samples may even require greater dilution amounts. So for things like crudes or tars or anything like that, you may actually do 1 to 100. Or if you're going to analyze additive elements in an oil, you may have to do a much greater dilution on them. On the right-hand side are sort of the more common solvents that are used. Kerosene by far is the most common solvent used. Advantage of it is it's relatively inexpensive. You can get it fairly pure, and it runs very easy relative to some of the other organic solvents. And how difficult a solvent is to run is related to the closely related to the boiling point. And you can see the ones that are listed there all have boiling points, fairly high boiling points. Kerosene is great, easy to use. Some of the others, depending on the sample, xylene is used as well. Not so much, maybe 15 to 20% of the people doing this type of analysis will use xylene. Tetralin, which is 1, 2, 3, 4 tetrahydronaphthalene, is also a good solvent to use. And then also you have MIBK, or methyl isobutyl ketone, which can be used. That's a challenge to use that solvent. You have pump tubing issues, and it really smells up the lab when you use it. So I have avoided that. I've primarily done kerosene and xylene are probably the two that I've used most in the past. Right? Advantage of the solvent dilution is you avoid the ashing procedure, so you reduce the potential for contamination. You're not going to lose volatile elements, and it's a very easy procedure to automate. Disadvantages: running organic solvents can be more difficult than aqueous solutions. Right? You can run into more issues. The solvents sometimes will want to put the plasma out, so you got to worry more about optimizing and tweaking conditions to run organic solvents. It may not dissolve the entire sample, and that's an issue with heavy crudes, tars, greases, and things like that. You may not get the whole the sample in, depending on what else is in the sample. The solvent likes dissolved light, so you may need solvents of different polarities to get everything in. So things like crudes and stuff, maybe the better approach is to do the sulfated ashing technique. That will completely solubilize the sample. And not all solvents are compatible with the ICP. You have problems, and we'll talk about it a little bit later in the presentation. The pump tubing, or you may not be able to keep the plasma lit. For some solvents, they're just so volatile that too much material gets up and the plasma goes out, and you can't do it. We'll talk about some things to get around to reduce that problem once we get into the nebulizer section of the presentation. Okay. And pump tubing compatibility, and we'll talk specifically about that also. Teledyne CTAC makes an automated prep station, so you can do pre-anal. It's a standalone system, so you can set it up and dissolve up to about 90 samples relatively quickly without any operator intervention. So it's ideal. The organic dilution is ideal for automation, and the system does that for you. And I've used it. It's great. It saves me a lot of time. I don't like diluting up a lot of samples by weighing them out. It takes me a long time. So this sort of gets me around that. Okay. Next, we'll talk about some sample introduction components that we have. And so we'll look at nebulizers, the spray chambers, torch, and pump tubing. Okay. So the most common nebulizer used for an ICP now are the concentric nebulizers. And they're used because they have very good long-term stability and precision. They have an advantage, they're self-aspirating. So what that means is they don't need a peristaltic pump. And the advantage of a self-aspirating nebulizer for this type of analysis is that if you have a solvent that you don't have pump tubing for, you can use the self-aspirating. You can just put the tube in the sample and the sample will be aspirated, sort of like what you would do on a flame AA. So you're not worried about the effect of the pump tubing being dissolved or getting soft and getting imprecise results. Disadvantage of the concentrics is they're prone to being clogged. The orifice on them is quite small. Things that will fit through the pump tubing, if the sample probe has a filter, things may still get by the pump tubing, fit through the pump tubing, but get clogged on the end of the orifice there. And they're fragile. So you have to take care of them. If what happens a lot of times, the end gets chipped, and then the spray is no longer straight, or you begin to cause it to clog. You find a point where the chip is, and things can clog on that. So you got to be a little bit careful with the concentric nebs. So because they're prone to the particulate matter, they're not a really good choice to do wear metals in oil, because you're always going to have some particulate. So there are other nebs that are better. But for clean solutions with organics, concentric nebs, they work pretty well. Right. The second neb that we've used in the past is the cross-flow nebulizer. This nebulizer is not used as commonly as it once was in the past. It has good performance, not quite as good precision or sensitivity of the concentric neb, which we can use the sensitivity issue as an advantage. We'll talk about that in a bit. Rather than concentric flow of the gas and the sample are at right angles to each other. We'll see a photo of that in a second. So it can handle more particulate matter, and it's not as sensitive. It's more rugged than a concentric. It's basically, what you see there is the end cap that goes on basically a Scott or a double pass spray chamber. So it's much more rugged than glass concentric nebulizers. So if we take a look at, the orientation is the sample comes up from the side, and the argon goes right over the top. And you can see that in here. This is the tube right here. It's a platinum iridium capillary in front of a sapphire piece there that has a really tiny hole in it. Argon comes through the sapphire crystal, and the sample is pumped through that platinum iridium capillary. Like the concentric, a cross-flow is also self-aspirating, so you can use that to deal with solvents that you don't have pump tubing for, but also because it's less sensitive than neb, you can also use it to analyze with more volatile solvents. When you combine that with the Scott spray chamber, we'll talk about spray chambers, but which is a little bit less sensitive than the cyclonic, then you may be able to run things with a combination cross-flow and Scott spray chamber that you couldn't run with a cyclonic and a concentric nebulizer. We use this for high level in aqueous applications, high levels of dissolved solids going from the concentric to the Scott because of the reduction in sensitivity with the Scott. You can run things at high level dissolved solids with that type of a setup that you can with the cyclonic spray chambers. Okay. The next neb type is a V-groove neb, and for the V-groove nebulizer that we use is designed specifically for organics. It's not meant to be used with aqueous samples. There are V-grooves that are available that will run aqueous and organic samples. Typically, a lot of times V-groove are used for high levels of dissolved solids in aqueous or HF type solutions. But this one is made of Riton, is machined from one piece of Riton, and the sample is pumped through this top tube, travels through and comes out this relatively large orifice. So any particulate that gets past the auto sampler probe or the sample probe that you're using, if there's a filter, as long as it fits through the pump tubing, it'll just come right out the sample orifice there and not clog it. And then the organic solvent drips down the V groove, and then there's a gas port right about where that laser pointer is, and that's what does the nebulization. Because the surface tension of organic solvents is lower than water, you get a nice even spray. On this neb, if you do aqueous samples on it, the spray is pulsy because the water is coming through as drops because of the surface tension. So it'll function with aqueous, but the precision is not as good. Okay, this requires a peristaltic pump, so it's not you can't use it to free aspirate. You have to have a pump on there. So you can't use it if you have a solution or solvent that you don't have pump tubing for or can't find pump tubing for. This neb is not a solution there. You'd have to go back to a concentric or a cross flow. And this is a tremendously rugged nebulizer. There's no parts to it. It's machined in one thing, so it can take quite a bit of abuse. They last a really long time. So for us here at Teledyne Leeman Labs, this is pretty much our go-to nebulizer for organic solvents. Right. Next, this is a different class of concentric nebulizers. These are the low flow or micro nebs. They have uptakes of anywhere from 0.05 to a half mil a minute. They're self-aspirating, so they're really good for volatile solvents. So you have something maybe trying to work with a solvent that you simply can't run when you use a standard concentric or any of the other type nebs. This one, because you're only putting in tens of microliters, a minute, you can run some tremendously volatile solvents with this. They have very high efficiency, so you would think that you would maybe see a big decrease in sensitivity. You don't. They're very efficient. It is possible that you virtually have no waste, that the entire 50 microliters a minute goes up into the plasma. There's very little waste, so they're good in that respect. And we've used these also to effect, so you can try and do things like naphtha, gasoline, some of the really volatile things that can give you fits when you try and run them conventionally. Right? There's also the ultrasonic nebulizers, and they'll be combined with the membrane desolvator. So you get to combine the efficiency of the neb with membrane desolvation, and it reduces the solvent load on the plasma, and you can get 2 to 5 times signal enhancement. So it's another type nebulizer that you can bring to bear depending on the type sample, especially if you're trying to look at really low levels in something. Okay. Spray chambers. So probably the most popular spray chamber used now are the cyclonic spray chambers, and these separate the aerosol by centrifugal force. So if you watch one of these, the sample is sort of swirling around in there. They're quite sensitive. If you take a cyclonic and swap out with a Scott, probably the cyclonic can give you up to 3 times better sensitivity. In organic samples like this for petroleum, that can be good, or it can be bad. Sometimes the cyclonic's too sensitive for that. And the cyclonics that we always use for organics always have, you can see this baffle in here, and that's used to try and take out, or sometimes referred to as a knockout tube, to knock some of the sample out so you don't have as much material going up into the plasma. Another advantage of the cyclonics is the volume is quite small, so you have fast washout, particularly when you're trying to do really high sample throughputs. Some of the other type spray chambers are bigger. Sample washout takes longer. And as I said, the models of these that have the baffle or the knockout tube in it are really the best for organics. If you don't have that in there, it's not impossible to get it to work, but it's a bit more of a challenge, and you run into more issues with carboning up and plasma instability. So the cyclonics are nice for organic analysis. So more traditional, older one is the Scott, or the double pass design. So basically the nebulizer is over on the right-hand side, like the cross flow, or you can actually, get an adapter, so you could put a V groove in there, or a concentric, all that kind of stuff's available. But the sample gets sprayed through the center tube. The big drops sort of impact on the end here, and they either get shattered into little drops or go out to drain, and then the smaller drops sort of migrate back and then up into the torch. So the smaller ones go between the outer wall and the center tube. It's less sensitive than cyclonic, so it can be an advantage when you're doing higher samples with higher volatility solvents. The larger volume, increases the washout time. So if you're looking for high throughput and you have samples that can be very high concentration, very low concentration, you could see some carryover from sample to sample. And that really, for us, was dealing with that to do sort of high-speed wear metal analysis is one of the reasons we started using the cyclonics back in the sort of mid-90s when they first started appearing. And we pretty much switched over where the cyclonic is now the spray chamber of choice. Okay. There are other types of spray chambers available. These also use cyclonics inside, but these are chilled spray chambers, thermoelectric Peltier chilling on them. There's two different types shown there from various vendors. The one up in the upper right is from Glass Expansion. The one below it to the left is from ESI. And these allow you to run the temperature of that spray chamber down, below zero, as low as maybe minus 20 degrees. And when you run that, so you're basically condensing out a good chunk of the solvent, and they work really well. When we look at the chlorine and silicate in gasoline, we'll see that we use one of these to be able to run the gasoline straight. On the lower right-hand side is a cyclonic that is basically a condenser. So you hook that up to a chiller that has a mixture of antifreeze and water in it, and you can chill it down. Not as low as these thermoelectric ones, but you can get down. So we've used those in the past. Sort of the disadvantage of it takes longer to get it down to temperature, and then if you have humidity in the lab, you get a lot of condensation on the lines and things. For me, the thermoelectric ones are the way to go, much faster. And some of these thermoelectric ones, if you have them and you have aqueous samples, you can actually raise the temperature a little bit, and that can help improve detection limits in some applications. So the cool spray chambers find a lot of use in this type of analysis. Okay. The torch for organics, I really prefer to use radially configured instruments, so using a vertical torch. It's possible to use horizontal axials, but I do find over during the day, if you're running a lot of samples, you can start to get a little bit of an oil buildup on the end of the injector, which can cause you some problems. Prefer demountable torches because I can change the injector bore. If you look on the right-hand side, there's 3 different injector boards there. The standard one we use for aqueous is on the left, 2.5 millimeters. An organic one is the 1.1, and then we have one in between. There's a 1.5. Most people use the 1.1 for the organic analysis. I really prefer the 1.5. I think it gives me better stability long-term, and I don't, even on a radial, you may still see a bit of that build-up on, bit of a drop that builds up inside the injector. I think that occurs less frequently with the 1.5 millimeter one. So that's what's nice about demountable torches. You can change the injectors. If you use a unit construction or single-piece torch, then generally the organic models of those have roughly about a 1 millimeter one, so they're quite narrow. I have used on unit construction torches that are meant for aqueous for organics. You just need to adjust your nebulizer pressures a little bit, maybe a little bit different position or gas flow, and successfully have done that. So I prefer the size in between there. So the 1.5, I really prefer that for aqueous for organic analysis. Right. Pump tubing can be pretty straightforward if you're doing kerosene. The PVC tubing you use for aqueous is just no good. It'll swell up very quickly and collapse. You won't be able to pump. Solvent flex or the yellow type tubing is good for kerosene. It works great for kerosene. For some of the other solvents, xylene, the Petroleum, and the MIBK, you need to go to Viton. Though I've always found that even using Viton with these solvents, the lifetime of the tubing is not very good. Normally within a day or so, you got to replace the tubing. With solvent flex with kerosene runs, you can run that for days and days before you need to replace it. Particularly for MIBK, I don't really like using it in the Viton. There's a material called Tygon MH. The only source of it that I know is glass expansion, and I've used that for MIBK. It really works well. It's somewhat costly tubing, but it really works well for MIBK, and you can run that MIBK for a few days, and it'll still work. It still work really well. So that's sometimes the limiting factor on the solvent that you're using is what can we use for pump tubing. Okay. Next, okay, we'll talk about plasma parameters, and so this is sort of one of the important things when you do an organic analysis. If you go from aqueous to kerosene, it's not that big a deal. You can run kerosene pretty much the same conditions you run water. You don't want to, but you can. So it's not as tricky. Some of the other more volatile solvents can be a little bit tricky. So the higher nebulization efficiency of the organic solvents, so you got to require some changes to the way you set stuff up compared to the aqueous. So the goal is you're going to set your conditions to maintain plasma stability, prevent carbon formation, and to get acceptable analytical performance. So for the methods that we're going to look at a little bit later, so the RF power is going to vary. Now the RF generator that we use is a 40.68 megahertz generator, so the powers that we use are going to be lower than if you use like a 27.12 megahertz generator. There you tend to run the organic at a higher power, maybe 1.7, 1.5, 1.6, 1.7, something like that. So they'll be a little bit higher. On the 40 megahertz systems, we generally run organics between 1.2 and 1.3. Very rarely do we ever go higher than 1.3. Haven't found it to really make any difference, and you really don't want to run too high a power because that can raises your background, can hurt your detection limits. So you want the RF power to be the lowest you can have it, and still keep the plasma lit and things be stable, right? Coolant flows, depending on, are not critical for the analytical performance. You just basically want to keep the plasma lit. So anywhere, what we'll see and the methods that we have here, anywhere from 12 up to 18 liters a minute. For me, my sweet spot for the coolant flow is about 15. That's where I like to run it. I'm not a big fan of low flow, so I like to run mine about 15 or so, if I can. The critical flow for me is the auxiliary flow, and that can be anywhere from 0.5 up to the max of 0.2. And that's critical so that you can prevent carbon formation. The auxiliary flow pushes the plasma away from the injector and away from the auxiliary tube. If it's too low and the plasma sits down low, you may have some carbon issues over a period of time. Can happen very quickly, can happen slowly over a period of time. And then the auxiliary flow along with torch position. So if you look over at the plasma discharge here, you can, I don't know how well it comes over through the internet, but the auxiliary tube is about right where the pointer is. So you want to maintain a little bit of spacing there. You don't want the torch to be too high up because the plasma is going to form where the coil is, not where the torch is. So if the torch is too high up, then that can cause you some problems with carboning. If the auxiliary flow is too low and the plasma sits down, that can cause some carboning. We'll look at what feature of the torch system that are used on this instrument. so that you can maintain the proper spacing when you take the torch in and out. Nebulizer pressure, that's going to depend on a few things. Well, what's the solvent that you're going to be using? What's the injector ID? So the more narrow the injector, probably the lower the lower the pressure is going to be, or the flow. And it also depends on the nebulizer. Nebulizers can run on different ones, and we'll talk about that in a bit. And the sample uptake rate, again, that's going to depend on the solvent. Some solvents you can, like kerosene, you can pretty much run the same, same uptake rate as you can aqueous. You tend to run it a little bit lower, and there are others that you're only going to be able to run, a half mil a minute or even less. And then when you get these really low maximum uptake rates, then you have trouble with the peristaltic pump, because the peristaltic pump isn't going to work when you only want to do 1/10 of a mil a minute. So that's when you try it. You might have to go to the free aspirating scenario, and it also depends on the pump tubing diameter. So for really volatile solvents, you may want to use really narrow pump tubing, so you limit the amount that you get up in there. Okay. So for the nebulizer pressure, the way I like to set it is get my torch in there, get my coolant flow and auxiliary flow set up where I like it, and then I increase the nebulizer pressure. So the green bullet, which is this, is just, and you can see it very faintly here, it may not show up, so it's just above the top RF coil, right? Some people like it a little bit higher, some people like it a little bit lower. I like to do it so it just is, when you look at it from the side, it's just peaking over that top coil. And then that's where I'll leave it. Then once I have the pressure set, then I'll optimize the view position, and we have a mirror on the system, which we call a source mirror. We'll optimize the horizontal and vertical positions using a 10 ppm iron at the 259 line. That's a typo. There is no 255 line. There should be 259 line. And that's sort of standard for us. We've always used iron to do that. And that'll give you a good compromise operating height in the plasma. Okay, right. Now, if you don't have very good conditions, then you're basically, eventually you're going to have some carbon build up. And if you look on the right-hand side here, you can see there's carbon building up inside here. I deliberately misaligned the torch and lowered the auxiliary flow for this, and let this go for quite a while. And then eventually the plasma extinguished, and you can see the buildup of carbon in there. This wouldn't happen to you during analysis, because eventually you start failing your check standards, because you're starting to block everything going through there. But you can build up quite a bit of carbon in there, and eventually that can cause your torch to melt. It gets the carbon there, even though there's not a lot, generates a tremendous amount of heat in there. And you can actually see this torch is showing some cracking or spidering because of that huge carbon buildup. If you have if you can't run, without, generally if your carboning is, I will always take a look at the positioning, or look at leaks in the sample intro, the ball joint between the spray chamber and torch, O-rings for the nebulizers. There's generally there's a cause. Sometimes it's a leak. Sometimes it's positioning. If you do have carboning problems, one thing you can do is add oxygen to the plasma, and that will prevent carbon deposition. It also reduces spectral emission peaks that you see in the 300 nanometer range. And you can add the oxygen can be added, via the auxiliary or the coolant flow. CTAC product VGX 100, or you can use you need a good quality flow meter, and you can hook up oxygen and tee it into your auxiliary, and you can go, and you only need mils per minute, 10 mils, 20 mils per minute, and that will pretty much eliminate your carboning problems that you may be experiencing. Okay, right. So next we'll step into looking at some of the methods that we've had. So look at some announced petroleum samples. So some of the applications that we'll look at. So we'll look at the analysis of a crude, diesel, and the fuel oil, additive elements in the oils, and the analysis of chlorine and silicon in gasoline, right? So crudes, we receive crudes on occasion, sometimes mostly from overseas. Crudes, really complex hydrocarbons. It's just lots of different type compounds in there, a couple of hundred, just sulfur-containing compounds. For the analysis, most of the time we're looking for things like vanadium, nickel, and iron, and then there may be some other trace elements that people may be interested in, right? And the presence of certain trace elements has an effect on the refining process and the product quality. For example, some elements are catalyst poisons. They want to know that. Some elements have environmental effect when the fuels are burned, like sulfur. When we look at additives, we may be looking at the QA and QC of new oils to make sure a particular product is still within specification, or in the on like condition monitoring or wear metals analysis, it can give an indication of the health of the additive package in a particular oil. Is the additive package still effective? So those are some of the reasons for some of this analysis. So instrument parameters. So you can see these are going to be somewhat repeated. So the difference here is, so we said before, I like to run everything about 1.2, and so these are going to be dissolved in kerosene. So 1.2 is good. We went really low on the coolant flow, and so that'll be probably the difference between these different applications that we're going to look at. The things that are the same for the crude, the diesel, the fuel oil, and the additives are going to be the auxiliary flow was set to 1.2, the nebulizer pressure 35, again, using the Riton, the V-groove, and the glass cyclonic with that center knockout tube. The quartz demountable, so in this case we used the 1.1 millimeter bore. And for this, since we did all of these, the crude, the fuel oil, and the diesel all on the same method, we used an internal standard. We put 5 ppm of cobalt in the kerosene and monitored that to correct for any viscosity differences between, because we're really the 1 to 10 dilution on the crude may actually have to do higher dilution than that. So we used the internal standard to correct for that. And the integration time we set to 30 seconds, which is pretty typical. It could go 15 seconds would probably work pretty well too. What we want to do is have some really good precision. The element wavelengths, these are all typical primary wavelengths for all the elements that we were taking a look at here. So sample preparation, so we diluted everything with kerosene that contained 5 ppm, internal standard, and we want to overcome potential nebulization effects. And that's one way you can add the internal standard. You can add it to the kerosene, or you can get a T and tee it in real time. That also works pretty well. There are some products available that allow you to do that, commercially available products. So we diluted the fuel oil and the diesel by a factor of 10. The crude was actually diluted by a factor of 100. We did all the samples in duplicate. The first we're going to analyze. The second we're going to analyze. The second we analyzed mostly to see what the relative percent difference between the different analysis was. Then we also spiked it with the multi-element standard so we could see what type of recoveries we get for these samples. Right? Calibration. So we diluted organometallic standards from VHG or LGC V23 by 100 ppm. This was all done on weight-to-weight basis, so, done with the scale, and concentrations from 0 to 10 ppm. So this just gives an idea of the linearity, so easily linear. You can see, and also the precision here is quite good using the Cyclonic and the V-groove nebulizer. That's pretty typical. I always like all my calibration standards to have RSDs, standard deviations of less than 1. I really like them less than about 0.5 if possible, but you see very good precision there. Okay. We looked at detection limits. So after we calibrated, we ran the blank back 3 times standard deviation of the calibration blank, and you can see the detection limits there are really quite good. very similar to what you would get in aqueous for most of these elements. You're looking at single ppb detection limits. So that certainly met the requirements that the end user wanted for this type of analysis, right? And so here are the results of the crude. Shows a spike recovery, so we're getting very good. We're getting 100% recovery virtually on everything. RSDs are anywhere from a couple of percent down to 0.4, 0.3%, somewhere around there. And the elements we would expect to be in the crude, we would expect some iron, some nickel, and some vanadium. So pretty typical results for a crude oil. Right? Fuel oil. Similar type results. Again, very good recoveries on the spike, very good precision, better precision than was on the crude. Again, probably because of not everything is solubilized. Maybe there's some particulate matter giving us some hassle here. So we're pretty happy with these type results. Again, these are typical results. Anything that says less than detection limit was below the value that was on the detection limit screen. So we did not detect some of the elements that were in there. And the diesel fuel, again, very relatively clean stuff. We found a couple of things in there, but again, very good spike recoveries and very good RSDs. Additive elements. We do a fair amount of work with people in this industry for additive elements. Motor oils, mostly heavy hydrocarbons, and the remainder is an additive package that enhances the oil's performance. So we add things are added to neutralize acids that may form, detergents, suspend the soot, carry away particulates. There's anti-wear, anti-corrosion things in there. And for an additive elements, the ones when we work with people, they're interested in the elements below: calcium, magnesium, sodium, phosphorus, sulfur, and zinc. Okay. Again, we look at these parameters, everything is identical, though this time this is a sample I ran, and I ran it at 15 liters a minute. That's sort of where I like to be. Auxiliary flow, again, was 1.2. Net pressure, same V groove with the glass cyclonic. And I, actually used a little bit wider bore, but kept the net pressure the same as before. Integration time this time was only 20 seconds. So slightly different parameters, but not substantially. The big one is really the auxiliary flow and the torch position, which would be the same between the two. Here are the wavelengths that we used. Because the concentrations of some of these are really high, we're using really, non-primary lines, particularly this calcium line and this zinc line, because the concentration of those elements are actually quite high. We did dilution. So in this case, we got a performance testing standard, which is available from VHG or LGC, and it's sort of a certified. You do the dilution, you run the sample, and then you send the results, and then you get your comparison of the results you got back. So we did a couple of different preparations. We also did, again, we did some spiking that because of the really high concentrations of some of these elements, we used a second standard, which is available, which is metal additive standard at 5,000 ppm. So we made some separate standards for that. Then we also did a separate standard for sulfur. A lot of the organometallic standards are made up in alkyl sulfonates. So if you want to do sulfur, you either have to have a separate preparation for that standard, or there are some samples that are standards available that are sulfur free. The ones we had were not, so we went and did that. Okay. Right. Calibration again. So in this case is because of the higher concentration of the additives, we did up to 200 ppm. Again, everything done by weight. See the tight precision. This is very typical precision with the V groove neb and the cyclonic spray chamber. As long as everything is set up well, it gets very, very good precision, just as good as you could get from a concentric for this particular application. So that's one of the reasons why this V groove neb is pretty much is our go-through. We determined detection limits, which isn't that critical when we're doing the additives, because there's always going to be some. It's very unlikely you're going to have none. in there, but you can see the detection limits again, single digit to double digit detection limits in ppb. So these detection limit capability is more than adequate to do the additive. One of the interests of this particular application was reproducibility from day to day. So every time we made up new standards every day and new preparations every day for this. So, and then we did analysis on day to day over 7 days, summed it all up. So if you look across, you can see the analysis is quite close on day to day, and that's a feature of the sample introduction system and the ability to take the torch out and put it back in the same spot, and we'll see that in a second. Then if we average the results over the 7 days, you can see they're all right around 1%, the worst one being sulfur, which was about 4%, but still well within the expected, the variability that the end user wanted. Okay, and talk about the positioning of the torch. So this is the position, this is the torch in the radial system. And so the way the torch is, there's a scale here that allows you to position it reproducibly. This whole assembly, right, there's a knob to adjust it, and then this lever releases it. And by moving this knob, you can move this up, and it's reproducible. So when I take the torch out, the torch comes out through the bottom. This whole assembly stays there. So when I take the torch out to clean it, replace the injector or whatever, when I put it back in, that black cylinder with the scale on it, it's in the exact same spot. So you get the same positioning. So it's good for day-to-day operations, or it's good if you have multiple operators. That way you don't have trouble when one person runs the analysis and someone else comes in, puts the torch in a different position and runs into carboning problems. So that allows you to have the same position in the torch on a day-to-day basis, and that's what helps give you the day-to-day reproducibility of the system. And that's so the torch disassembled here. It's a demountable torch, so you can replace the injector, or you can replace just the coolant and auxiliary flow. And the gas connections are automatically made when you put it in and turn it. Gas connections are made, so you don't have to worry about manual connections. So these samples were they're certified. So here were the certified values, and then here are the found results, and these are all within the range of acceptable values for the certified standard in there. You see again with the spike recovery was quite good, and with the RSDs are really quite good also. Okay, and the final application is the analysis of chlorine and silicon and gasoline. This was done for some users that we have in China. They were going to be requiring the analysis of chlorine. Okay? So gasoline is a fuel made from catalytic cracking, crude oil, mostly for internal combustion. Really complex mixture. There's 500 different compounds in there, with all sorts of carbons in there and different boiling points. So it's a relatively complex mixture, right? So the presence of certain elements can have a bad effect on the gasoline. For example, copper and zinc can cause oxidation. There are some anti-knock compounds in there. Lead's not really used anymore, but there's some of the concentrations that potentially that can be in there. The user wasn't interested in really any of those. They wanted chlorine and silicon. And chlorine, because organic forms are corrosive to the metals, can also cause problems with fuel injectors if there's chlorine in the gasoline. Silicon contamination can cause oxygen sensors in the engine to give false rich signals and causing the engine to run lean. So the sensors got to be replaced, to prevent poor performance on the engine. And the limits that they want that are going to be set in the People's Republic of China is going to be 1 ppm in the gasoline. So 1 ppm chlorine, 1 ppm silicon. Right? So halogens by ICP. ICPs generally operate, from 165 up to 800, 900, or 1100, like ours do. Best wavelengths for halogens, chlorine and bromine, are in the 130 to 150 range. So you need a special setup to be able to get down to that range, and the Prodigy Plus instrument has an option for that. skip to that. So what we do is we take our normal optical system and we mount a camera, another camera on the top of the optical system. And then basically there's another spectrometer, which is on the bottom. So over here, there's a grating, so the light hits a grating here, and then a mirror, and up into the camera, right? So sort of a side view. So the plasma is over here, over on the right-hand side. So the light comes in. There's a source mirror here. This is the mirror we use to switch between axial, radial, halogen views. It also allows you to optimize the position in each one of those views. Our instruments have had this. We call it a source mirror. Our instruments have had this for forever. The light hits that through the slit. Then there's a grating light for the halogens. Then there's another mirror, and then up into the halogen camera. So the range of that is roughly about 130 to about 150, actually 135 to about 155 nanometers, and that allows us to get both chlorine and bromine with the same measurement. And here's a photo of the instrument in my lab, and here's the camera assembly that sits on top there. Right. This one's a little bit different. I had to go to a little bit higher power. We're running the gasoline, increase the coolant flow a little bit, keep it lit. Auxiliary flow, had to max that out to keep the plasma pushed forward. You notice the nebulizer pressure is much lower. See that and why that is in a minute. And also the pump rate was much slower. Gasoline's much more volatile, even though we were using the cooled spray chamber. We still had to back everything off a little bit. Use a different type nebulizer, the Teflon nebulizer, concentric design, but that's what's used for this the cool cyclonic spray chamber, the PC3LT, low temperature. We ran it down at -20, which is the lowest temperature it can run. Ports demountable, and went back to the 1.1 millimeter bore again. With the gasoline volatile, so we're doing everything we possibly can to reduce the amount of material getting up into the plasma. We integrated the halogens for about 30 seconds, and we integrated the silicon for about 10. Right. Here's the sample introduction. So it's the PFA 100 nebulizer. It's sort of a mic. It's a micro neb. Doesn't have a lot. Doesn't consume a lot of sample. And you can see the cool spray chamber here again set down to -20 degrees. There is a spray chamber, cyclonic spray chamber located in the front here. That's what chills it, and it's got insulation and things around it, and chills down. It chills down very quick. Within 5 or 10 minutes, you're ready to go. So it worked out pretty well. Here is the setup in the lab. We also, this time, we would, to be able to get the halogens at 1 ppm, we needed to use the axial, actually a dual view system, but configured as an axial system. So you can see that we use a silicone transfer tube to get the solution, the vapor up into the plasma. Close up of the torch. When we used the chilled spray chamber, there was just no issues. Everything is set up just the way I like. Be able to run it full 8-hour day, no carbon, no plasma shutdowns. So you can see there's not a lot of space between the end of the discharge and here. That's why I've got it set up for 2 liters a minute. You know, I'm really trying to push that forward. Sort of constrained on where the torch can be relative to the air knife, and that's for the halogens. The intensity changes quite a bit if the torch is further back, or the air knife is further away. So this was the setup that gave us the intensity, the sensitivity that we needed, but it was quite close. But again, we didn't get any buildup of carbon. And if we did get some, then we would have brought in the oxygen. We didn't need to do that. Okay. So we did calibration standards made up in gasoline. Conistan, we got 5,000 ppm chlorine, and LGC V23 900 ppm made standards from 1 to 5. And for the gasoline samples, no sample prep, no dilution. We just ran the gasoline straight. Made trips to the local mobile station 87 octane. We can get E10 here in New Hampshire. The customer really wanted E15, but that's just not readily available in New Hampshire at this time. So the 10% was fine. We worked that out. Here's the silicon calibration. Get calibrated from 0 to 10. Precision's anywhere from 0.2 to 0.7. And you can see the way the data is collected there. Solid state detector. Here's the peak where this green rectangle is. We measure the peak there, and then the background correction is done simultaneously. Those two off-peak regions in there. Oops, I'm sorry. So we did silicon at 2 different wavelengths, 288 and the 251. Same idea, 0.1, very good precision on that. Here's the chlorine. From again 1 to 10, precision was anywhere from 0.8 to 1.6, a little higher than I normally like, but chlorine in the gasoline can be a little bit tricky. You can see we did much wider background points. That helps with any changes in the level. We're averaging, rather than to one or 2 points for background correction, we're actually averaging about 10 different points, and that gives us better capability to measure at the lower end. And we did 30-second integrations. So first we needed to do we want to get an idea what the detection limit was. So in calibrated, ran the blank back, 3 times standard deviation, 30 seconds for the chlorine, 10 for the silicon. So we're getting just under a 0.2 ppb detection limit for chlorine, and we're getting 3 and 4 detection limit, ppb detection limit for the silicon. So we're good. We should be able to make some measurements at 1 ppm with this. Like the detection limit to be a little bit better, but for now it was okay. Sort of without the plasma being on, you can get an idea. You can see how close the tube intermediate or the auxiliary tube is. That's why I'm using the higher auxiliary flow. And you can see this purge tube to the instrument actually extends through the knife. There's an air knife here to cut the top of the plasma off, and that helps keep this quartz cool so it doesn't melt, even though it's actually in the plasma. So when you want to run chlorine, you want to make sure there's no air. So even that little bit of air that would be coming in through the knife here, which doesn't affect normal wavelengths, like it doesn't have any ill effect on the 167 aluminum line or the sulfur or anything like that, but it would make a difference for chlorine, for halogens. So we extend that in there, and that allows us to have essentially no air. There's no air getting in from the plasma into the entrance optics of the instrument, right? So we analyzed the gasoline. And there was really no chlorine in the gasoline that we had. So we spiked it in just under 1 ppm and did a bunch of readings. We're on the sample 20 times. We did a number over some different days, and we can see that we're able to make measurement at 1 ppm with about 6% RSD over that time, which was acceptable to the end users. And we can see the spike values for the 2 silicon lines are actually quite close also. So it's a good application. We have some systems over there that are currently doing that. Again, using the cool spray chamber is really what allows us to do that. One thing we could always try is to use one of the micro nebs without using the cool spray chamber, but we never really got back to doing that. The results were acceptable with that setup as it was. So that was sort of the conclusion to that. Yep. So with the cool spray chamber, which allows us to do the gasoline without any other sample prep. So just go right from the pump right to the test tube, and you can go ahead and run it. And the torches, the demountable design with the small injector, we're able to do that without any carbon buildup, which was a big concern with the gasoline, but has not been an issue. And I think that brings us to the end. So we looked at some sample intro information, some sample prep information. Hopefully the information here will be helpful to you if you do this type of analysis, or help you work through some problems that you have if you do this type of analysis. So thank you for your attention.